I'm, as mentioned before, senior security researcher sorry, at Contrast Security. This talk is about modifying bytecode at runtime for fun and profit, and mostly for security, because that's kind of what I do now. So let's get started. So the instrumentation package that's used by all Java agents is relatively new. Well, it wasn't at the start. It's been there since 2004 and expanded in Java 1.6 a few years later. Pretty much all kind of instrumentation that you might see in Java, so like the J command, JConsole, JVisualVM, JMap, etc. Use it. Anything where you would specify a process ID to connect to uses the instrumentation API, as well as third-party tooling. So things like Jacoco, test coverage, which we probably use in, if you don't know that you do, anything that shows test coverage probably uses a Java agent at runtime. Of course, contrast, assess, and protect products. I have to do this because they're kind of paying me for this. Use a Java agent. I'll talk more about those later on. So there's two ways to use a Java agent. One is at startup. So you essentially specify a -Java agent path as one of the startup parameters in Java, or you can attach it after the process is started. So I'll go through the dynamic attaching first. It's fairly simple, surprisingly. So this is what the code looks like. Very minimal version of the code anyway. So you have virtual machine. This is basically just the code. So you specify the process ID of the process you're attaching to, the location of the jar file that will be loaded by the process you're attaching to, then JVM detach, and that's it. And then the code that gets run within the JVM you're attaching to looks like this. You have an agent main method rather than a main method, and it executes whatever code you like. So that's pretty simple. However, under the hood, it gets quite complicated quite fast. Because you're doing inter-process communication between the target JVM and the agent you're using to attach to. So take a look at it. It's a bit of a weird setup. So actually it changes based on the operating system and what implementation of Java you're using. I'm just going to show you what it looks like on Linux and using Oracle or OpenJDK. So the attacher JVM creates a file under /temp called attach PID, name of the process that you're targeting. Then you send a SIGQUIT signal, which is a termination signal to that process. This has to be done by the target and attacher JVM have to be of the same user. You can't be doing this from a different user, which is one of the main security controls that are in place. Because you can't just do this to any JVM on the system that you're on. You have to be the same user. Send a SIGQUIT, which is similar to a SIGINT, which you do with Control C. I forgot what the actual command is now. Anyway, it does that, and then the target JVM gets that SIGQUIT signal. And rather than quitting, it looks for a file, the file that was created by the attacher JVM with its process ID name under /temp, realizes that's what's happening and does something else. It creates an attach handler thread, then creates a socket, which is used for inter-process communication between the attacher JVM and target JVM. And that's then used. Then the attacher JVM connects to that socket as well. and then passes the load agent argument, as was seen previously, and that gets injected into the target JVM. Well, the target JVM loads that jar from disk. Then from that agent jar that was loaded, looks at the manifest file, and the same as what you'd have with a main method in Java, it looks for that. It looks for a agent main in the manifest. I'll show that in a second. Loads it and then loads that agent main method. So this is what the manifest looks like for the agent jar. There's a few interesting things in here. So you have the pre-main method and agent class. So agent class is what we saw a minute ago with the agent main method. And later on you'll see it attached statically from the startup. Anyone's like, yes, attached. So when it's attached statically, it uses a different method name of pre-main, and so that's what's used here. And you have the class mentioned of control security JBOM, which will be coming up in a minute. You also have a few extra permissions. Can redefine class and can transform class are similar. It's an odd kind of thing in the agent. There is two things that basically do the same thing. There's transform and redefine. So you can modify the bytecode. You can either modify the existing class or replace it. But you could always just modify the existing class enough that it essentially becomes a new class anyway. Not sure why there's two of those. I believe it's something to do with performance. And then there's set native method. So if you know about native method calls in Java, you'll have a native method name, which then links to C code with the same name. So if you want to do instrumentation, because native calls can't have Java code in them, the instrumentation wouldn't be able to do anything because it's essentially an empty method name, kind of what you get in an interface. So this prefix allows you to change that name and still reroute back to the underlying C code. Not really used that much unless you care about native code. So let's go to the first demo. So JBOM is the agent we'll be using. So this is something created by Contrast Security. So to give a bit of background about this agent, so what this does is it creates a SBOM, or software bill of materials. This was created earlier on this year. So after the log4j, log4shell stuff, and then other issues we've had, security issues that have been quite common throughout the industry. One of the big issues that teams have is working out what applications they're using that actually contain the vulnerable versions of log4j, for example, in your own code or in just applications that you manage, so things like Jenkins or Jira, Confluence, those kinds of things. And so knowing what you need to upgrade is most of the problem a lot of the time. So this creates a bill of materials. This creates a list of, essentially a list of all of the dependencies within your application in the Cyclone DX format, which is an open source format. That's what this does. So first of all, you can see this. What I'm going to do is run this command. Nope. To get a list of all the Java processes running. So we need the process to attach to. So this is the process. Add this. And then this will start up. And if I attach a debugger, to attach here, run that. So I can skip past most of the code. So this is similar to what we've shown earlier. What we're doing here is creating connecting to the JVM. load the agent path, and if at this point, so I'm attaching a debugger here to the, I've got a debugger attached to JBOM, but I'm also going to attach a debugger to the application I'm attaching to, so you can see both sides of the code. Because you've got this code which does the attaching, and then the actual JBOM code is loaded into the target JVM and then run from there. So you have to attach to both. So with that, go back to protection, hit play. It should then load the agent into the target JVM. It does, and as you can see, it's hit the agent main method. So if I hit play again. So this is what you have. You have a list of arguments passed in from the agent JVM, which in this case is the location of the JSON file we'll be writing out to. And then the instrumentation API is also here, is also here as well. So hit play, good. So the only thing in here we're really using is we're getting a list of all of the classes in this JVM. So that's one of the main selling points of JBOM. This is free and open source, and anyone can download it. There'll be a set of links at the end. Is unlike other applications that generate a SBOM, it does it at runtime. So you don't get. So when you think about what libraries your application is using, you have things injected at build time. You have other things that are build time but not at runtime, so things like JUnit test classes. So those are at runtime, so those are ignored. But you then also have things like third-party dependencies included in app servers like JBoss, BuzzFeed, Tomcat, etc., or other plugins that are added at runtime. And so JBOM gives you those as well because it's attached at runtime. It gives you all of the things that are running then. So this will give you a list of classes from the instrumentation API. So this is all running within the target JVM, not the agent, the attacher JVM. List of classes, goes through all this. Generates that list of all of the jars. It will then look through the manifest files of all those jars to find out what the artifact ID and group ID is, and then generate a JSON file from that. We can then take a look. If anyone's curious. You can see this is a Spring application, which I'll be going into more detail in a little bit. Spring, so you can see Jack's annotations 2.13.3. So it's been able to attach the JVM, pull out all of this information, and then output it to this JSON file. So that's what happens when you attach dynamically. Let's go back to the presentation. Cool. Okay, so that's dynamic. There isn't much difference in the permissions. You can, assuming permissions are set correctly on the JVM, you can basically do anything from runtime that you can do statically from startup. It's much easier under the hood for static attaching because all you're doing is on startup specifying a Java agent, then location to jar. There's no issues with setting up the inter-process communication. It's all done within the same JVM. And essentially the only difference is the method name. It's pre-main rather than agent main, but then you get the same argument list and same instrumentation API access. And then again, referenced by the pre-main field in the manifest file. So the main part of this is, well, the fun part is talking about Rasps. Rasp is runtime application self-protection. It's in Java, it's an agent, but in different languages, it's injected in different ways. So a Rasp will protect your application at runtime. So, for example, if you have a exploited SQL injection vulnerability in your application, it would be able to look. It would be able to find that SQL injection and protect and block that SQL injection or deserialization or path traversal, whatever the vulnerability is. This is usually done, and this is how and Protect is a good example of this, by analyzing the data flow between the entry point into your application. So if you think about what we're showing in a minute, Spring Boot, Spring already, isn't it? You'll have an endpoint, you'll have a entry point into the application, usually a web request goes in, comes in. That's classed as kind of potentially vulnerable data. And from that point, it's then tracked through to various potential sinks, which could be like a database request or a command execution or deserialization or accessing a file on disk even. And it would then look at that data that came in from that request to see whether there is a potential, if that's being actively exploited. So it's trying to break out of the path. So by adding .. .. to the file name, for example, it's trying to access a file it shouldn't be accessing. And at that point, it will then block that request and usually just throw an exception of some kind. So this blocks certain attacks. I can't show you Protect source code for, I'm sure, fairly obvious reasons. So I've written a kind of a demo Rasp which will protect against a Java deserialization attack. Might ask, what's a Java deserialization attack? May not be the best kind of attack to create Rasp for. So with Java deserialization, what happens, and serialization is the Java object is converted into a byte array of a set format and then sent somewhere, and then another JVM, or even the same JVM, reads that data and reinstantiates that object. And the problem that can cause is because that format contains both the data and the class it's meant to be rebuilt. If you can essentially recreate, if you can, as an attacker, you can change that class name and you have access and you can specify what the data is. If there is a class on the class path of that application, which can do weird things when it gets reinstantiated, you can do stuff. These are called gadget classes, or gadget chains even. So when that object's reinstantiated, first, the no-args constructor is called. So if there's anything in there that you can do something weird with, you can do something. Or there's a magic method in Java serialization called readObject, where essentially it was there to allow the developer to, how to put this, set things up again. So if you have an object that, for example, connects to a database, so you can set all those fields correctly when it's reserialized, but that database connection or IO connection won't exist anymore because it's being written to disk, recreated, and then it's gone. There is no database connection. So that was kind of creative to allow you to then get that information, recreate a database connection or whatever else it might be, and then that object then works as you'd expect. And that's fine until someone can do something with that. And that's what people have found over, I think, it started in about 2010 when people realized that this was potentially a security vulnerability. And then since then, people are finding kind of these gadget classes that do have weird side effects when you set the right data. And if you can essentially, as a user, send a Java object to a JVM, there's, depending on how updated that Java, the libraries in it are, you can sometimes get a remote code execution. You can always get a denial of service. There are certain kind of patterns you can add to a hash set with lots of links in between it. So when it gets recreated, it essentially uses up the CPU basically forever. So you always got denial of service, but you can always sometimes get other weird side effects, remote code execution. which I'll be showing in a minute. So a while back, I created something called Flakerizer, which is based on a attempted fix in Java, JEP 290, which I'm sure everyone knows, which was added to Java 9 and then kind of backported to Java 8 in a weird way. And this didn't really work very well. I mean, it worked fine if you did everything correctly and you knew about it, but no one did, and no one would ever use it correctly. So essentially, you could create a whitelist in a properties file saying all of the classes you're meant to be able to deserialize or reserialize on your friend. And that's fine if the developers do that, but then who the hell would? And if you knew there was a problem with it, then you wouldn't use Java deserialization in the first place. So it wasn't great. So I've created a library which, so if you look at the code at the top, you have vulnerable code where it's just deserialized. It's regenerating that object, another class, from the data, which is a byte array, I imagine, which is fine if that data is actually another class object. But if it's something else, then you potentially have a security vulnerability. But at the bottom is my version with a filtered object input stream. So what you do is you specify the class you're expecting, and it will look through that data to make sure that that class is there. And only that class or values within that class, because obviously that class could have another class in it, and so on and so forth. So it creates essentially a graph of all of those, and creates a whitelist of all of those, and nothing else is allowed through. This hopefully would block this kind of vulnerability. Which is fine. So if we take a look, this is the endpoint we're going to be attacking. So this is, I'm sure pretty much everyone here can understand what this is. So this will create a post request endpoint with a message body of base64 encoded data, and it will deserialize that data back into a Java object, hoping that our object is called another class. If it is, that's fine, but if it isn't, then you may have a problem. Just remember that because you may really think that because we're casting it to another class, that happens after the deserialization has occurred. So whatever attack happens before the casting, so that doesn't help you. And that's the fixed version. So let's get on to the fun stuff. So restart this. This is the Spring application I created to demonstrate this vulnerability. Start this up. So if we take a look at the demo, this is the controller class. So there's two endpoints, one with the filtered object input stream. Let's get over this. Make it a bit more visible for people. And one without. So let's generate the payload. So this creates a process builder object, serializes it to base64, and so what will happen if I go to that class? Obviously, this is a made-up class I've created for this purpose, but there are this is based on something that has existed in the real world. So what will happen when this is reinstantiated, this process builder class, it will call the read object method, or the deserialization functionality will call this method, and we'll be setting this value, the CMD value, which will be a command, and that will then set the command and then execute whatever command that was. So if we then hit running, so hopefully this will work, usually does. Send this to POC Java, and then hopefully, yep, we've got the calculator application to appear, showing that we've executed an arbitrary command. But show you what it looks like when we use this version, which should be safe. No, use this one. Turns an error page, and if we look, you should see a stack trace. Filter status rejected. It's an invalid class type, and the command wasn't executed. So that's fine, but you might be asking what the hell's got this to do with agents. So I've created an agent, which what it will do is it will go through, on startup, it will modify, it will look for the object input stream read object, look for whichever class it's being cast to, and then modify that method to essentially make it look like this one. So instead of being an object input stream, it's a filtered object input stream where we're specifying the class name. And if we can do that correctly, it should effectively remediate this vulnerability in this application. So let's kill the application. And good. So we restart it up with the Java agent. One thing to note if you do something like this yourself, if you put debug on, put the debug command before the Java agent command. Otherwise, the debug will start up after the Java agent, so you won't be able to attach to any of the Java agent code that's run. So there we go. So bring this up. Hopefully. Good. So it started up. And as you can see, we have a pre-main method. No arguments, so that's null, and the instrumentation API. So if we jump to the next point. So what we're doing here is we're adding a class file transformer, which is our implementation of the class file, well, the deserialization file transformer, which is an implementation of the class file transformer interface, and adding it to the list of transformers. And so when you have anything in that list, when each class is loaded by the class loader on startup, it will be passed to the method in that interface. So if we jump ahead, and I've just realized I didn't put a debug on the next step. So let's kill that and start again. So this is what the method looks like. Put debug there. So adding it to the list of transformers. And so this method here is called on the class load of each class and startup, and then throughout the life of the JVM if any other classes are loaded afterwards. So what we're doing here is we don't want to transform every method of every class in the JVM because that would take forever. So first stage is to ignore all Java-based classes. We'll assume they're safe and make sure that the object input stream is actually being used within that class. Because if it isn't, we don't really care about it. So we'll put a breakpoint into that if statement. We should get, and then we'll start getting something in Spring is using Java deserialization, but we don't really care about that. So if we set we know what class we actually care about, so we'll just add it to this. Play. Wait a second. Okay, so we found the class that we actually care about, the controller class, which contains those two methods, one runable, one not. So next stage is to tell you about the library we're using. So what we get here is a list of the byte, a byte array of the class file. So that's essentially just the .class file you'll have in for every class. It gets added here, and assuming you have permission to modify classes, which is set in the manifest, you can then return it. If you return it as it is, nothing changes, but if you change that byte array, that's what gets loaded instead of the original class. So what we're using here is called ASM. It's fairly low level for what we need to do. It's kind of the best one. There are other libraries you can use. ByteBuddy is probably the best one. It's a bit higher level than ASM, but if you want to do relatively simple things like just instrumenting methods, it's probably the best thing to do. But we're doing something a bit weirder. In fact, ByteBuddy uses ASM under the hood, so you can just think of it as a helpful kind of layer above it. But the Asm Framework is what we're using. What this will do is it will take the class file as a byte array, pass it through the reader and writer and any adapter we've added. It will read that class, go through all of the methods, all of the values in it, and you can override methods to visit those methods or fields or lots of different things. We kind of care about methods, so that's what we'll be overriding. You can then modify the instruction set and do what you need to do, which we'll be showing in a second. And then afterwards, it's written to disk. I should say, no, it's returned. I'm also writing it to disk just so you can see it in the new version in a IDE, because otherwise it looks just like gibberish. So if we go down, so this is the class visitor implementation we've created, which is boilerplate, and then the method adapter, because we need to look at every method to see which ones are using an object input stream, and the ones that they are, we need to then make some changes to the code. So we'll start from here. Read object is present. We don't care about other methods. So if we look at this, so on visit end, so you have visit start and visit end. Visit start we don't care about, but visit end you can modify the instructions, the list of instructions. So we take a look at this. This is the list of instructions. I'm not entirely sure how easy this is to see for this method. And yeah, you're probably not going to understand most of that. I don't either. So we've got byte array input stream, instruction, byte array, blah, blah, blah. Lots of stuff. So if we jump down to the next part. So what we're doing, because with this, we need to work out what the class, the object input stream read object is cast to, because it's starts as object, but you generally speaking don't want that, so it gets cast to, in this case, another class. We need to read that value, because that's what will be put into the for the object input string constructor. So we need to know what that class is. So that's what this bit of code here does. So we're looking for a check cast instruction, and then so we want to know what that is, and so we find that the check cast instruction, then go back to the previous value and get the cast value, the value it's been cast to, which in this case is another class. So now we have that. If we don't have that, this Rasp does nothing. So if you're not doing any casting, it doesn't really work. This is very much a demo. It's not meant to be used in production by anyone. This was pretty much created for this kind of talk. So yeah, don't use this. Use something better, like contrast protect, which doesn't work this way. It works in an actually better way than this. So then what we're doing, we've got the cast. We then need to find the, okay. Method, okay. So we need to check for the object input stream constructor. So I think what happened was the previous method was the filtered object input stream. We're looking for the object input stream constructor here. We didn't find it, so it jumped over and gave up. So if we go back, so we have the constructor. And then here we want to change that constructor because it was object input stream, but we don't want that. So we get that. We want to change the description from object input stream to filtered object input stream. And the owner, which is the same. The description of the constructor, so it's going from a input stream interface to an input stream interface to and a array of classes. We're setting the name to init, pretty much what it was. So we've modified that, but we also need to, so we've modified the constructor, but we only need to add the values into the constructor. So what we need to do is here, create a new class array with one value of name of class, which would be another class in this instance. So put static, create a new array, duplicate that array, put that in the put field, which is the put it into the constructor, and then this is the value of that array, which will be the another class, and then L. I think it's an element in an array. It's just the format that's used by Java, Bytecode, and then store that array into the constructor, and then we insert that. So we insert that at the end of the constructor, so it adds it to the end, where previously it was just the object at the input stream. We're now tacking that onto the end of this list of array, this array of a single class, and then accept, which just passes it back to the Asm library, and that's it. So if we hit play, there'll be a few more, but we can just ignore those now. And then that's it. So it should have, so we go back to the top, it would have done this. The reader, which just jumped over, has accepted it. The writer would have taken that list of instructions and recreated that class with that set of instructions. And then that class has now been passed back to the class loader, and that would have been loaded instead of the original class, hopefully. We've also written that to disk, just so we can see it. So if we go back to the deserialization demo, so I've written that to, the root of the deserialization demo project. And so we should be able to see the controller class. So this is the modify. So we have the original Java. That one should be unchanged, but this one is different. Where you have an object input stream, and if we look at this, so this one unchanged, but with this one, it's now filtered on object input stream. So this is what's been loaded. This is the class that was loaded by the class loader on startup. And so hopefully, if we run the original vulnerability here, instead of it popping up a calculator, it should just do nothing. I was hoping to do something. Let's kill the debugger. I think that's doing something wrong. So send it again. And as you can see, we now have a stack trace where filter state is rejected because we've modified that bytecode to remediate that vulnerability. Obviously, this is a fairly simple demo. Well, the code isn't simple, but It's just fixing a single deserialization vulnerability with an application, but the power of kind of runtime protection is much better than that, is much greater than that. There's not just deserialization, lots of different vulnerabilities can be detected and fixed at runtime, even ones that aren't known about ahead of time. For example, if you know about some of the issues that Atlassian software's had when Protect is running against it. So the remote code execution vulnerability that was found about a month or so ago, which is kind of funny because it's just essentially all you're doing is at the end of the path / variable name equals Java command and then processed then code to run, and it will then execute that. This and Protect would protect against that because it's protecting against known vulnerability types rather than specific vulnerabilities, and so you get protection against essentially a lot of 0 days. So things like Log4Shell was mostly remediated ahead of time because it knew about GND and I injection and would block it if it came from a user request. So you get those kinds of protections built in. You also have different. So the other thing from a security point of view, which I think really requires its own topic, is IAST, which is interactive application security testing. Essentially, you have a Java agent that instruments the application in a test environment, and you run your usually integration tests against it, and it can detect potential vulnerabilities in that code. In the same way that Protect can find the source of the data from a user usually, and syncs. It does that during test and reports back to you when there's potential vulnerabilities, which also works really well. But it's a bit more thorough than Protect. Protect is meant to be run in production, and kind of like IASs are meant to be run during test because it's a bit slower. You don't necessarily want to that running production. And that's near the end of the talk. There's a list of links of the code I've just talked about, and also Contrast Security / developer. We have lots of free tooling you can use. Static analysis. There's you also get a trial of things like Protect and Assess for your applications, which I recommend. Obviously, I'm paid to. But yeah,